Seems to be working. Yep. Okay, so today we're going to take a look at dimensionality reduction further, namely nonlinear dimensionality reduction, or this part of the class was called neural network 3 for a good reason, because the nonlinear dimensionality reduction is realized through a neural network. And before that, I'm sure you're all kind of curious. Most of you would have had a quick look at your quiz results. So here's an overview. You get a distribution plot from Grayscope as well. This one is slightly more detailed, so to speak. Again, the goal of this quiz is essentially not to give you a harsh grade, and just this is some feedback about whether you are following the breadth of material that we're covering or not. So out of the class that has still about more than 190 people enrolled at this point in time, we have 182 submissions. As you can see, most of the class sits here. This is where where half of the class is. It's hard to get a perfect score. Again, most people have done reasonably well. As I said, I do not expect this to have high correlation with the exam, and close to the exam will give you a bit more information about how to prepare for that. And assignment 1 is due in 2 days. I hope you guys are doing well and progressing along. So Meng Yan have also, since last night, the close of the quiz, have done a few graphs about how the class as a whole has been doing. So we're going to talk about some of these apparent pain points, or where about 40% of the people got it wrong. First of all, question 13. This is really about conditioning of Gaussian, Journey Gaussian distributions. The correct answer is highlighted on the screen. So one thing about this quiz, or how Grayscope works, is that you have to get all the answer right to get that point. For this particular quiz, it's really, I feel it's minor because it's only 2% at all. So if, in case you missed one due to omission, yeah, don't feel too stressed about it. The point here is if XA and XB are jointly Gaussian, and we condition on one of the variables XB, the mean can be really either way, right? So on the right is like a figure from week 2, I believe, Friday workshop, where the mean of XA is really here. And then depending on which value of XB we're conditioning on, right? If we're conditioning on the red line above, the condition mean is above the like marginal mean. If we condition on a line below, such as here, as we can see, the conditional mean is sort of less than the original mean, right? Right, the question is conditioning the other way, but it's essentially just swap XA and XB or in business. The other insight we would like to get through to you is that if for jointly Gaussian variables, if the two variables are not uncorrelated or independent, they're the same thing for Gaussians, not the same thing in general, then conditioning generally reduces uncertainty or reduces the variance, such as seen in this particular picture. And the geometric intuition is that right? If we take the projection of one of the axes of ellipses versus if we take a cut of the ellipses and measure the spread, like taking the cut has a less spread. So I guess this wasn't, we mentioned it in the workshop, but it requires you to sort of think about the intuition of what conditioning means. And I feel this is a useful exercise, and hope, in case you didn't get it, hope you get it now. For those of you who got it, good job. So question 12, it basically asks, right, whether the eigenvalues that we compute in principal component analysis are guaranteed to be positive or not. As we said on Monday's workshop, right, for symmetric matrices, the eigenvalues are guaranteed to be real. For covariance matrices, the eigenvalues are guaranteed to be non-negative as well. We didn't prove it in the workshop, or I don't think textbook has an elaborate proof as well. But I think this is worth knowing. Like, you're like, one should be expected to show that covariance matrix, like a covariance matrix of a data set X, is positive semi-definite. It's not hard to show using the definition of positive semi-definiteness. I leave that up to you to do. Question 4 is another one. So naive Bayes, the model, as we covered in the classification lecture, it deals with discrete features because for continuous features, it will be hard to compute P of X condition on Y equals to 0 versus P of X versus Y equal to 1, right? And in the naive Bayes assumption is basically says features as assumed to be independent condition on the class label. So here we essentially have the D's dimension of feature X or kernel function X. And in here, feature X makes a lot more sense. So think of it as, say, probability of words given spam or non-spam. Question 11, someone asked on Piazza as well. So this is slight variations of what's covered in the textbook and in the lectures and workshop. So in here, we essentially have a X squared activation function rather than a 10H in the textbook. So the 10H was an odd function, X squared is an even function. So for even functions, if we flip the signs of the input weights, the output don't change. That results in like 2 to the power of 1 different Wei symmetries. So the answer is actually the same as the number in the book. It is a large number of Wei symmetries. So that's all about the quiz. So here is what we're really planning to talk about today. Given that we talked about component analysis in general, I feel it's, so this lecture is broken down into basically one core technical component, and then a number of what I call culture things, many things that we will talk about the setting, problem setting, and briefly about the model, but you're not required to reproduce proofs. Or sometimes we won't even talk about like what exactly the solution is. It's sort of a giving you exposure to different variants of machine learning models related to what we talk about in terms of component analysis. So the brief mentions include independent component analysis, or ICA, and sparse coding. We will talk in a bit more detail about autoencoders that are essentially, let's say, the marriage or joint application of two ideas. One is associative networks. Again, its name, associative network, is essentially a two-layer autoencoder or two-layer network, as we will see. So this is in a book. And then the other idea is basically the idea of many layers. This has different names. We talked about neural network, but in last week's workshops, we didn't talk about how to be deep, where deep is in all the rage nowadays, as you know. So what is the good reason to be deep? And then a few practical tips to make it all work. So in here, I would say that there are way too many practical tips to cover. So we just cover a handful to give you a taste about how to mathematically build intuition about neural networks. If you really want to use this for your research project or some large data set you have in practice, then you need to look up, let's say, neural network documentation a lot more. Okay, this is a taste. And then we will talk about application to autoencoders, various applications in image processing and also in recommender systems. Actually, this is one paper that I did with a few collaborators a few years ago. So the goal of this is to not only motivate autoencoders to tell you what are the different things a seemingly simple mathematical concept can be used, but also to give you exposure to research literature, meaning if we move beyond the notations, then the exact descriptions from the book, how you can use what you already know to sort of consume this new knowledge, so to speak, right? Okay. So we talked about principal component analysis. Independent component analysis is just one word different, but it's almost a completely different setting. But it's a fascinating setting. It's designed to address what's called a cocktail party problem. If we have K people talking at the same time, well, just imagine a cocktail party, right? So there are many different sound sources that are more or less independent of each other. Let's say people talking with different timbre and pitch of their voices, men and women, and there may be music playing in the background and so on. And we have at least K microphones. Basically, we have at least many observations as the number of sources we want to model. What's unknown is this mixing matrix A. Basically, what it says, the observed data X is a linear combination. So this is sources, and this is mixing and unknown. So as you can see, this is quite useful. But it also seems hard, right? How do we solve this thing where we don't know what the source is and we don't know what the mixing coefficients? We're also assuming for sounds, it's a reasonable assumption to assume that the different sources are linearly superimposed on top of each other, right? So, and this problem is called blind source separation. It's blind because we don't have either the mixing or some knowledge about the source. And what we can assume, but what we can do is to put a number of statistical assumptions to help us sort of make this problem sufficiently constrained so that it's solvable. So at most, one of the signals is Gaussian, which is usually the noise component. And then if we assume we just wanted to recover the source and the mixing component, but don't care about the amplitude of the source or even the sign of the source, and we don't care the order of the recovered signals. Basically the same way symmetry and permutation argument we've seen Right, so the matrix A is at least rank K and can be inverted, assuming it's exactly K by K. Right, so when sources are no longer Gaussian, one thing to know is that uncorrelated variables are not necessarily independent. We just know that they are independent, but they're not uncorrelated. So we wanted to find A such a way that the objective, loosely stated, is basically we want the columns of S are maximally independent and minimally Gaussian. What is interesting is that despite sort of S being non-Gaussian and coming from independent sources, but the columns of X, the result of the mixing due to central limit theorem, tend to be Gaussian-like. So what this hints is the objective function will have a mix of, say, a description of the Gaussianness in a high waving manner, and also minimizing the mutual information or some information measure between the different source vectors. So that's that. We're not going to be able to cover the methods of ICA, but it's a fascinating area. Some of you have started sending me emails saying, hey, I have this other problem in my research or in my engineering. What kind of, but classification or regression don't quite fit. What should I do, right? So this is also the reason why we talk about these diverse sets of models to give you some exposure about what other models can potentially be used. If you have those questions, you're welcome to email it to me. You're also welcome to participate in a pilot of data science machine learning bootcamp in this. Essentially in computer science, we're starting that up with a number of researchers who are very experienced. The goal of that is to basically help people to use machine learning to make their own scientific discovery in their own domain, so to speak. If you're interested in that, also get in touch. All right, so let's jump right into the main content of today, associative neural nets or autoencoders. As the book illustrates, associated neural network is what looks like in this figure 12.18 is just a two-dimensional neural network. As usual, we omit the constant features or bias. What's curious here was, if we remember from last week, the input are called x's, the hidden layers are called z's. The output should be y's, but here it's instead of being y's, they're being x again. So what's going on, right? Why do we want the input and the output to be the same, right? So there are, I think, one crucial reason, or actually two reasons. One is, the first one is we want to learn crucial features, right, from input X. So if you have been paying attention to machine learning press in the last few years, more than 5 years, the current claim or so-called in the deep learning era is that you should learn features rather than craft features. I would say not every application begs that, but basically trying to automatically learn a feature representation, such as these z's, that are a function or sometimes complex nonlinear function of x that are useful for classification rather than trying to specify your own kernel basis or trying to do feature engineering. That seems very attractive, right? And it has been effective for many domains, from speech to general sound to images and other things. and time series and so on. The second one is the feature Z here basically is what we call reduction in information, right? From X. Well, graphically, we're going to talk about this again, so don't worry if it doesn't make sense just yet. Graphically, we have less number of Z's than we now have the dimensionality of the input. The intuition is that, okay, we're doing some processing by learning a deterministic function on either of the layers, right? So we cannot invent new information. We can only lose information. And one way to make sure we have information reduction is to have less number of dimensions. So the notion that we can only lose information by processing is actually quite an important one. It's called the information processing inequality. We're not going to again, formally cover this here. It's an information theory, and also I don't think the book chapter 1 has it, but it covers the core concepts that leads to that, right? All right. You might say, oh, now what happened between the last page and here? It's basically the reduction, right? So this was called Z1s through Zms, and then we just added one more hidden layer. And the book makes the distinction of basically one layer network, right? So the claim here is even with nonlinear units in a hidden layer, especially the sigmoid function, the one layer associated network is equivalent to linear principal component analysis. So it might be easy to see, let's say, if both of the layers are linear, we get back principal and component analysis. Because if we use square loss between the input and output, and we constrain for example, let's say in extreme case, we just want one hidden unit Z1. Then from the argument we went through on Monday, the best projection that guarantees minimum square loss is the Z1 being the projection to the first principal component of inputs X. So and we can basically envision Z1 through Zms like progressively. Although for neural networks, due to the way space symmetry is enforcing the like the bases being orthogonal and the input and output bases being transposes of each other, might need extra work, right? So the book has this claim that even with nonlinear units, it's still PCA. So let's just say we trust the book for now. And then if we add one more hidden layer, as we said in the neural network workshop, if we just look at the front part of the neural network, due to the universal approximation theorem or result of general neural networks, so neural network with one hidden layer in the middle and nonlinearity can represent any function. So in here, if once we add one more layer, we basically generalize this mapping from X to Z to any nonlinear mapping, and the Z back to X as any other nonlinear mapping. All right. And the geometric intuition is as follows, basically from the space of X. let's say here in 3 dimensions, we map it to a lower dimensional z, and then from the function f2, which is realized by the reconstruction part of the network, here, which is also nonlinear, we basically map a subspace in Z, let's say a square to a curved square in the original X space. So this is essentially the core idea and implementation of an autoencoder. You already know neural networks, so you know how to backpropagate the weights through many layers, right? So the key idea is quite simple. So why hasn't this seen a lot of use until the last, let's say, 5 to 8 years? That's because a number of considerations on how to exactly design and implement so-called deep networks of this kind. In here, I say deep because, let's say, loosely speaking, 2 layers is not called deep in this class. But now we have 4 layers of weights. Okay, so that's deeper than 2 layers. So in order to understand that, let's first look at the reasons of having more than 2 or a handful of layers. So again, this is sort of a cultural exposure for this kind of argument. There are 3 references here. So the basic argument is functions that can be complexly represented by a depth k architecture might require exponential number of computational elements to be represented by a shallower or k-1 layer architecture. So basically, shallow networks will need a lot more and exponentially many neurons to represent the same function as the deep architecture. This does not contradict with the universal approximation result, because that result basically states if we have sufficient number of neurons, we can represent any function. Now, this is a bit deeper in the sense that, what is the kind of number of neurons that we are expected to have? So again, one example that may help us to build some intuition into this result is assume we would like the d-bit parity function, where the d-bit parity function is for an input of a binary input vector of length d, we would want to compute the parity bit, where the parity bit is basically if there is even number of ones in the vector, then it outputs 1 and 0 otherwise. This function is very useful in digital communication. Well, it's everywhere now, from the internet to your phones and so on and so forth. But it's also hard because in order to compute this, we literally need to touch every single bit. And also, basically, any bit changing its value will affect the output of this function, right? So the theorem behind the parity function is that a d-bit parity circuit of depth 2 would have exponential size. This theorem or result is due to Andrew Yao, a Turing Award winner, a great CS theorist, and Hastad 1 year later. So Yao's paper basically sets the upper bound of implementing such a parity check circuit, and Hastad 1 year later. So like FOCS and SODA basically are the top conferences in computing theory. Hastad established the lower bound for small depth circuits. So these results are really nice, and they made it into the practice of deep layers on general functions almost 20 years later. This also says how long it takes for theoretical results to sort of translate to significant applications, where here we refer machine learning into application. But the translation between, say, machine learning algorithms to real applications could be a lot faster than this. So an overview of this result was narrated in Yoshua Bengio's paper in 2011. And Yoshua won the Turing Award for deep learning 2 years ago in 2019. So then you might ask, what are these deep layers doing, right? So there's lots of tools to visualize the different neural network layers, even online. So here is, again, an illustration from Yoshua Bengio in 2009. What it does is say, if we're doing image analysis, and we put each little image patch like this through a neural network, it will basically, and we have many layers of such what's called convolution operators, you will basically get higher and higher level representations. The initial representation may be edges and corners, and then we start seeing shapes, and then after a few layers we start seeing objects. And in this particular example, it says, well, after a while we might see events such as men and sitting. And by the way, there are, for computer vision researchers, there's lots of ways of them essentially inserting themselves as illustrative examples. For example, the Bishop book has his family. This picture is believed to be Bengio himself, or his younger self, so to speak. I believe that because staring at the current picture of him or the more recent picture of him, it does have high resemblance. So if that's the goal of deeper layers, to learn essentially compositions as higher and higher level representations, we're not gaining, basically we're not having free lunch again. So we're not gaining expressive representation power for nothing. It's because deep architectures are harder to train than just a two-layer network. The issues include that they get stuck in local minimum and plateaus. And then it's observed that it's hard to obtain good generalization performance and hard to initialize random weights. In fact, we covered some of the reason of these last week on the Friday workshop. If you missed it, you can also look at the Medium post that's pointed to in the workshop notes by Kapasi. It basically explains why, there is a good mathematical reason why initialization is hard. And for a long time, actually, when I first encountered machine learning, the conventional wisdom at that time in the early 2000s is that one or two hidden layers seem to perform better, and there's no reason to go beyond two layers because two layers have universal approximation properties, and they're easy to train, right? But then at that time, neural networks tend to overfit, and it's not really performing better than other competing methods, such as kernel methods, which we will cover in right after the break. So around 2006, a breakthrough came that figured out how to make deep networks work better. And there are researchers, including Bengio, Hinton, and others, are connecting the dots about, for example, the theoretical paper about the representation power of deep layers and the practical tricks on how to train. it's also curious, the neural network hidden layers tend to be called distributed representations for, I guess, not particular strong reason. I think it's called distributed simply because the different neurons look like they are independently well, they're activated by different sets of weights from the same input, right? So this word don't really mean distributed computing. Well, it's another example of overloaded terminology. So the secret there is so-called unsupervised pre-training, which involved a lot of autoencoders and related architectures. So we're going to talk about autoencoders a bit more, but let's just take a moment to reflect what has deep representations become, right? So this is a standard picture of convolutional neural networks. A lot of you are taking computer vision at the same time. You probably have seen this by now in that class. So for those of you who have not, what this visualizes is the deep architecture of, say, convolutional neural networks or architecture for images, from natural images to medical images and so on. It's right now typically there are two basic components in what's called the first generation convex for image classification. It basically have these convolutional units, basically a neural network that work on small patches of images, and then you move the patch along the image. This also is equivalent to essentially share weights between different parts of the image, right? And then there are the stride is basically how much you move the patch at a time, and then there's a pooling operation basically for images. There is a spatial extent, but at the end we want, say, if there's a dog or a car in the image, therefore we want to do some spatial aggregation. The common aggregation that we do is max and min, and in classification, max pooling seem to work well in practice. So there's multiple, as you can see, there's basically what's called convolutional layer filtering, or doing different sets of neuron weights, followed by pooling, and then do so again. And if you doing so a few times until we get to a stage where we can just stretch out the image into a vector and call essentially plug in the vanilla neural network, multi-layer neural network there. It's called dense layers now. Basically, it's called dense because all the input is connected to all the hidden units. It says two dense layers, and then at the end we get a classification. So there are the visualizations of this is basically earlier layers are edges plus colored blobs. After that we have textures, and after that we have object parts such as parts of the clock, eyes of the dog, wheels of a car, and so on. And then at the end we have objects. Right. So around 2010, networks like this need to be pre-trained with autoencoders, right? So the picture down here is called stacked encoders, and it's essentially the same picture we saw a few slides ago from the book. Basically, there is a bottleneck, what's called bottleneck hidden layer, or the hidden learned representation. They were called Zs. The input layer is X. The output layer can be X prime or Y, depending on what we're looking at. So the autoencoder is trained to use function CS to encode the input into some representation C of X. The codec output of the autoencoder is, we can think of it as itself or variants of itself. Right, if the again, the hidden layer, if it's nonlinear, then the autoencoder behaves differently from PCA. The one limitation from PCA is that both the hidden, the PC dimensions and the input are assumed to be Gaussian, right? So if we have a strong reason to believe either of them are not Gaussian and have multiple peaks, so it seems that like nonlinear multi-layer autoencoder would be a good idea. So what would be a loss function? So this structure is basically the model description, as we have exercised a few times in supervised learning. And then the loss function here can be just the reconstruction error, right? In other words, so the L is some error function. And then we wanted to compute the error between the input X and some function F. So that covers the reconstruction part that operate on the hidden distribution, hidden representation C of X. So F chain with C of X. Compare that with the input X is the loss function. Hopefully that's intuitive enough. So here we're just talking about the cost function a little more. Right, as we said, F of C of X is the reconstruction produced by the network, the both parts of the encoder. Minimization of the negative likelihood of the reconstruction gives the encoding C of X. Basically, if we take the log of probability of X given C of X, that could be an objective function. If X condition on C of X is Gaussian, then we recover the square error, log of Gaussian is square error. If the input X are binary, then we recover the familiar cross entropy loss, right? We can also think about C of X as in different layers. Basically, if the input is X, and then we can have C1 of X and C2 of X. And then we can also break down the reconstruction as this layer of, which layer is, right, so this layer is F2, and this layer is F1, function F1. And we just call this stacking autoencoders. So stacking, deep, more layers are essentially the same concept. Again, if we run this on images, there are visualizations about what the stacking layer learns. We talked about this already, from primitives to paths to objects, in this case, faces. So it's worth talking about what all the kind of things people try to use autoencoder for, right? So these features may be useful for supervised learning tasks. So between roughly 2006 and 2011, the preferred way to training a deep neural network is to do unsupervised pre-training, or in other words, train an autoencoder on your input and then cut the reconstruction part off, and then just use one of the hidden layers as features for supervised training. As we can see, the autoencoder does learn sensible features, and it seems to work. It works a lot better than just two-layer network at that time. So that's very encouraging. So in here, there is also a blurring of terminology about supervised and unsupervised learning. So in this case, I would say it's really a crossover. So therefore, when you encounter supervised or unsupervised in the literature, just be careful. There is no blanket precise definition of supervised versus unsupervised. So I say this because this can be seen as unsupervised because there is no y, right? There is only x. And z is like c of x. I can also say that this is supervised because there is an explicit error function to require f of c of x is sort of roughly the same with x itself. This can be also called self-supervision in the literature. Yeah, the rest of the slide we just said discarding the decoding layers, and then we can directly use Z with another supervised learning training method. In here, a supervised training method is basically a target. It will include target variable y that's not x itself. Where self-supervision, we're just supervising x with itself. So various pre-trained networks are available online. So in here, I will clarify by saying that these pre-trained network are they use essentially supervised end-to-end training. So they don't have an autoencoder stage. As again, those of you taking computer vision would know that networks such VGG19, ResNet, and all the state-of-the-art models these days have more or less ditched the unsupervised pre-training stage because practically just use the signal to train from end-to-end seem to work better. The same also applies to natural languages. In their self-supervision, meaning given a chunk of text, basically predict the word from its surrounding words or predict the next word. And then you can use parts of the network to do other things, such as classifying sentences, classifying documents, parsing the sentence, labeling part of speech, and many other things. All right. So as we kind of said, training deep networks and initializing is difficult. So here's one concrete mathematical trick that will address what we mentioned last Friday about neurons saturating. It's called Xavier initialization or Golarod initialization. It's actually a funny name because Xavier Golarod was working with Yoshua Bengio in 2010, and they published this paper that was written in 2009, I believe. So the community really took this on and ended up planting both his first and last name as the name of the method. Right, so the problem of saturation, as a reminder, is basically when we operate on the flat spot of the sigmoid function, or say the ReLU activation function, the derivative is 0. So if this happens in some later layers, the gradient that propagates back is also 0. This will make essentially this neuron dead and unable to influence any of the previous layers to reduce error at all. So we will want to avoid the neurons operating in these bad spots. Right? So for each layer, actually, when we initialize all the weights across all the layers, we need to be careful that they don't hit the bad spot at the beginning. Right? So if we assume that the input is distributed like standard normal, this is not such a crazy assumption if you remember what we said about PCA can help you whiten the signal, and you also center the data before you do PCA, so you can do this. Even if you don't do PCA, one standard trick is to what's called using Z normalization in the, it's called in data mining. But basically for each of the input dimensions, if they are continuous, subtract the mean and divide by standard deviation to make at least the marginal distribution of each input dimension look like standard normal. And if we assume that the weights are initialized as a normal centered around 0, which makes sense because look, if we do if the x is centered around 0 and the weight centered around 0, then the output will also be centered around 0. And therefore the activation, let's say linear activation, is basically inner product of the input and the weights. Now we're wondering what the variance of activation is, because if the variance is too big, let's say greater than 5 or 10, then a large portion of the output for, say, remember the probability mass within one standard deviation is about 68%. So we don't want 1/3 of the activation to hit the dead spot, right? So if we compute the variance of Z, it as like a combination of X and W, we can see because X and W are independent, they're both 0 mean. Therefore, the variance is essentially the expectation of the product. And because they're independent, we can pull them apart. It's basically M, which is the dimensionality of the input, times sigma squared. Right, M times 1 times sigma squared, M times sigma squared. Right, so if we want the variance of Z to be small, let's say 1, if the variance of Z is 1, then it's very unlikely the activation value will go outside of +5 and -5. We can just set sigma squared to be 1 over M. So after some simple algebra around Gaussians, we derive, or actually Xavier-Gollerot derived this really useful heuristic for optimizing weights. Basically, make the standard deviation of the weight inversely proportional to the square root of the number of input dimensions. Then it takes care of to have nice back propagated signals initially, at least at initialization. You get to practice this in the lab. So have fun. So you might say, what about after initialization, right? During different rounds of back propagation. So there are other tricks, such as called clipping gradients, to make sure that the weights don't move too much in a round. I don't think we will cover that, but just be aware that other tricks exist and look them up. Let's spend the next half an hour or so talking about application of autoencoders. So we'll cover 2 bigger classes of key applications. And then if there's time, we might cover sparse coding. If not, we'll just drop it. Is there any questions so far? Nope. Everyone happy? Great. So let's first talk about denoising autoencoders, which is a rather powerful concept. So we said for autoencoders, we essentially want the input and output to be pretty much the same thing. In here, denoising autoencoder is such a neat idea in that it basically says we want the output to be the clean version or the desired version of X that we want. The input can be a noisy version of it. And if we do this, what's neat about this is that, so we have, let's say in training time, we can have lots of clean images of X. And then we will want to, in the real world, right? The real world gives us, like, in here it's not only Earth, right? So it's like, let's say, due to Earth's atmosphere scattering, like if you do satellites images, or if you have a picture from Mars, because of imaging conditions and transmission, it's really noisy, right? So we have noisy image. And right, just to denote the noise. So how do we train this thing, right? So we can actually, it's much easier to add noise. And under mild assumptions, you can make the added noise similar to the real noise and get some in X prime. And then you can use your synthetic, essentially, noise added image X prime and X pair to train the autoencoder, and with the hope that the hidden representation will represent essentially a clean version, right? So the noise hopefully will be removed after we do f of c x prime, right? So we want x to be f of c x prime. So that's cool. So this is an intuitive picture about how this works. The first paper that does this is actually pretty simple, but it really works. If we, okay, yeah, even with this low, like I guess low resolution copy of the noisy and clean pairs of image, we can see that, well, this is at training time x prime, and this is x, and this is the output of the image after being processed by what's called stacked sparse denoising autoencoder, as proposed in this paper. So this was a NeurIPS paper in 2012. It was the paper at the right time because image denoising has been a problem or technical problem that's been tackled for 20, 30 years. And at 2012, deep neural networks or stack autoencoders was just sort of known to the wider community beside a small circle of people who invented them for 1 or 2 years, right? So applying a new tool and obtaining better results than traditional methods is quite nice. Before this, one of the common or classical methods is called deconvolution, where it doesn't mean deconvolution in deep network, like neural network sense, which is basically transpose convolution. It means essentially, if we assume noise is essentially a linear filter, then we essentially derive the inverse filter. So this is the culture part of this workshop. I'm just going to take essentially the core part of the paper and let's read through it a little to understand what the approach really is, right? So on the top, so this is page 2 and 3 of the paper. If you are trying to read a research literature, usually in the machine learning paper, the model, quote unquote, model section is where you get the gist of the information and the rest of the things you can skip. Of course, when you start out, you read like the intro and everything else. Especially if you don't know the problem domain, it's worth reading the intro. But given that we just cover what the problem is in the past 10 minutes, we can just look at the model section. There is a model architecture on top to help us understand it. It kind of looked like what we were staring at, except the width of the neurons are different. So it basically has a, yeah. It says, Y is the original noise-free image, and X is the noisy image. It seems that this one operates from left to right rather than the other way around. But the arrows go the other way. But anyway, so there's a bunch of layers in between X and Y, and there are 2 paths that look symmetric, so that's okay. And we're looking at like a squared arrow function here. So that's nothing really new. And f equals argmean of the square error just means we want to find a good neural network. And then it has this part about denoising autoencoders that already exist before this paper. If we look at it, it's basically saying, oh, we first want to, so if we look at this, this is essentially a neural net layer with a layer of weights and bias, and then a nonlinearity. And then the next part is basically another layer on top of h of x. Right, it's basically two layers that we get y hat. And then we just compute the error. So that's good. So what does it mean by stacked sparse denoising autoencoders, right? So if we just stare at this, this part is square error. It's nothing new. These two parts are L2 regularizers that we saw for a few times from regression to neural networks. So they are nothing new. The only new part is this KL divergence part. This must be what they claim to induce sparsity. Okay, we're not going to go into this because I haven't exactly told you what KL divergence is. It's sort of a distance metric between distributions. You can read about it here or in textbooks. Yeah. And then there's some more detail about how you initialize and do the learning. So, and then they talk about experiments. So in other words, in about 3 minutes, we would have read this paper and understood it. Of course, this paper was very timely in 2012. If you're writing a NeurIP submission now, and it looks like this, you probably won't get accepted. So this kind of model is very useful, right? It's not just, when we say denoising, we really mean in a general sense. I wouldn't call some of the following things noise in images, but you can kind of see that, well, the same architecture applies, which is very nice, where the same model can solve drastically different problems. In here happen to be all images. We can ask, oh, what can this do for resizing image, either resizing up or down? You may think that, oh, I do image resizing all the time on my phone by pinching it and zooming it and so on. And I don't even think about it. This doesn't mean that resizing is a solved problem, or at least the signal processing folks may have thought it's solved, because if we look at the frequency view of resizing, we're essentially getting rid of high frequency components. But this is what happens, right? The best prevailing method before neural network came along was called bicubic resizing. It's basically applying a polynomial spline on the frequency components. And so the difficulty about resizing, especially upsizing, is that, again, we cannot invent new information, but we still want the upsized image to look nice. So operating in the frequency domain is nice, but that don't totally correspond to how our eyes work, right? So as you can see, there are some artifacts, especially around the child's chin, from this resizing. But with the neural network, autoencoders, we can essentially learn like the low resolution and high resolution pairs of images, where we both have ground truth for, again, using self-supervision, and then give a new image, ask it to invent the high resolution image. So needless to say, the stuff on the right looks better. We can also deal with corrupted images. Like if there's a bunch of text on an image, we can essentially invent the training pairs of such images in an unlimited fashion, because we can put text on known images. And then we ask the neural network to denoise, or essentially just hallucinate the version without the text. So this is also a demonstrated use case in the same paper. It can do that. So that's rather nice. You can also edit images, right? This is called in-painting, which is a very nice application that was emerged in the late 90s and early 2000s in image editing software such as Photoshop and others.
Sorry, I think you're muted for a couple of minutes.
Sorry, but I think he's still muted.
Okay, sorry about that. I don't know what has happened in the, in Teams that it keeps muting me. Just checking that people have heard me talking about this image denoising in-painting paper, but you possibly have not heard me talk about the applications. Is that correct? Right. So in a nutshell, basically we can feed the denoising autoencoder different variants of the images in order to achieve different image processing applications, such as upsizing an image without inventing new information, or undoing text on the image where the input is the version with text, and we can generate lots of training data for that, and the output is a clean version of the image, or basically adding small annoying objects in the image and asking the denoising autoencoder to remove it, right? Yes, you have heard a bird. All right. So is there any questions about this whole denoising autoencoder and in-painting part? Nope. Then let's move on to our second major application, which you will probably have to do in your assignment 2, which is being written right now. You will have done some autoencoder in the lab, and now you can use it for recommender systems. I guess I was lucky enough to be part of the team that wrote one of the first papers to use quote unquote deep approaches for recommendation. And this was a 2-page paper at the World Wide Web conference. We felt like, oh, it's nice to have such a simple paper published, and the idea is really simple. This turned out to be one of like the most cited papers for all of us nowadays, which is quite surprising. It goes a long way to say that the simple approaches that works goes a long way, right? So first of all, the recommender systems problem. Let me just expand on this graphic a little bit. So like in recommender systems, assume for the moment that we're trying to recommend movies to users, right? So we have this what's called sparse rating matrix. Let's call it R, right? And each row represents a user, and each column represents a movie, an item. Right, the traditional approach since about 2007 or so was to do matrix decomposition, which relates to like singular value decomposition. So sort of a relative of PCA for non-square matrices, is to say R is approximated by, yeah, I'll just write it in the same row. Like a user feature matrix of, do we have of k dimensions, and then also an item feature matrix of the k dimensions. This is matrix factorization. In particular, this is incomplete matrix factorization because a lot of the entries in this big R matrix are unobserved by definition. No one can watch all the movies, and the point about movie recommendation is to recommend stuff that you haven't watched to you, right? So one intuition here, there is a feature learning component in the traditional approach already. So each user, we can see that the score, right? So the score Rij, if we call this big matrix R, this matrix U, this matrix V, is an inner product of the user matrix, basically the feature of user I times the feature of item J. Roughly speaking, there's also some bias term and so on. So you can see, oh, we need some features that's conceivably low dimensional. In the movie recommendation literature, people have looked at, for example, clusters, or basically each dimension of these features and items. The intuition is that they're corresponding to user and item types. For example, users who like adventure movies will have a high inner product with items that are adventure movies, right? So users could, like stereotypically, let's say, cluster into people who like romance, adventure, horror, and so on and so forth, right? So this is quite well suited for an autoencoder. What Suresh, the PhD student at the time, he's now working at Twitter and recommender systems, did was to just plug in an autoencoder. If you look at the paper or this graphic, you will see that so the input is a vector. We'll talk about what the vector is so far. But basically, the objective is some square error of this autoencoder model that we will talk about, plus some L2 regulator term. And this is quite standard. And the graphical illustration here is if we have an input vector, we're essentially passing it through a set of weights using linear algebra plus some bias term, which is denoted as mu. Is basically the mean of the input or the mean of the projection, passing through an activation function, passing through another set of linear layers, and then another activation function. So basically this outer part is the reconstruction part of the network, and the inner part is the projection part of the network. You say, oh, this is all nice and good. We've been talking about individual entries in the rating matrix. Now you need a vector. What do we do, right? So the paper tried two approaches. Basically what's called user. So the options, the simple options are basically taking the columns of this matrix versus taking the rows of this matrix as input. Turns out taking the columns work better because in these benchmark data sets, such as movies, almost every movie has some watch, but then there can be users with not a lot of data at all. So the what's called item-based autoencoder for recommendation work better. Right. So this is like a stair of the notation a bit more. So there are two projection matrices, V and W. And then this rating vector of item I, at least the observed version pass through V, and then we try to reconstruct it in the W. And there's bias term. The plate notation here, the box, means we have n, like basically multiple of this rating vectors. It's basically corresponding to our book notation of xn, right? So weights are tied across all input data, and the reconstruction function is simply basically g of v times r plus some bias, and reconstructed using w times this whole thing plus some other bias passing through another f. So you might say, what kind of activation do you want to choose? So this paper tried sigmoid identity and different combinations. We found that having sigmoid nonlinearity in the projection helps, but having it at the reconstruction doesn't quite help. Right, this is root mean square error, lower is better, and just not having nonlinearity doesn't help. And surprisingly, it beat like all of the prevailing approaches. Bias matrix factorization was what I drew last round, and then RBM restrictive Borel machines was the prevailing neural approach at that time, and Lorma was the some local projection approach. So I believe in the homework you will be able to work on this smallest of the data sets, basically movie length 1 million entries. Which shouldn't take a lot of time. It's just a few dozen users and a few dozen items. So we're 10 minutes before our time is completely up. Is there any questions? And do people want to hear a little bit about sparse representations or not at all? Okay, yes, since we have a few minutes, we might as well talk about something new. So the idea, we've been talking about mapping from x, a vector, to c of x, another vector. So the idea about sparse representations is that we want most of c of x to be zeros except a few. Why do we want to do that? Because the intuition is that only a few activating features is easy to explain, right? Or this is good for interpretation. Right, given a long text document, we wouldn't want to describe like how many words it have in a vocabulary of 10,000 or even 100,000. But we can easily describe it as, oh, this is a sports article with a reference to local politics or something. That's easy for humans to understand, right? So the mathematical way to express that we only want a few non-zeros in the code is our zero norm, right? In sparse coding, right, so here's, again, the culture bit where we just talk about stuff, is we're still using the L2 reconstruction error, and we want, the notation here is a little bit messed up. There's W and there's alpha, but basically the basis functions are phi still, and we want the combination weights being essentially the code word C. We want the alpha combination weights to be sparse. And our zero norm, if we remember the definition of LP norm, is basically, let's say, alpha, our zero norm is basically alpha to the raised to the power of 0, and then like, okay, 1 over 0 don't really work. The piece norm is basically raised to the power of 0, and then summed over different dimensions, and then raised to the power of, like, take the piece root. If p is 0, we can see that the inner part is basically alpha 0 is 1. 1 if alpha is not 0. And then operate on different dimensions, and then if it's 0, then it's 0, right? So the other note is that these basis functions don't need to be orthonormal. They can be what's called overcomplete, where the notion of overcomplete looks like this. So this is orthonormal basis, and then in this space I could have, let's say, 3 different bases that are at the 120 degree with each other. Then this is overcomplete, right? So we're like, something raised to the zeros norm is difficult to optimize. Therefore, we relax this and choose a different value of P. In this particular case, we're essentially substituting L1 norm into where the L0 norm sits. So this corresponds to what if we do lambda times alpha L1 norm, then it corresponds to Laplace prior. So L2 norm corresponds to Gaussian prior on the weights. In here, it corresponds to Laplace prior. Note that this Laplace is the productive scientist. This is not the same as Laplace approximation that we didn't quite cover in the regression, but it's in a book. So that was like a square approximation to distribution. So the Laplace prior is basically exponential distribution on the weights. So again, sparsity, in terms of sparsity assumption, we will want like alpha 0 to be small. And then we measure reconstruction error like this, which describes the objective function on the last page. And L1 norm is convex. We talked about convex last week on Friday. Having convex functions is generally a good idea. L1 norm is convex, but not everywhere differentiable, but there are recipes for that. So the one argument that people working in sparse coding have made, which is like in what cases that minimization with L1 regularization give the same solution as minimization with the original L0 regularization. This is called the exact recovery scenario. It's a nice thing if we have this. So the last page basically talk about when exact recovery happens. If we know the exact minimizer that satisfy the L0 problem, let's say alpha star, and it has like basically less than 1 over m entries being non-zero. If alpha star satisfies the stronger condition, then the minimizer of the L1 relaxation has exactly the same sparsity pattern as the alpha star, right? So same sparsity pattern meaning which of the entries are non-zero, not exactly the same value on each of the dimensions of alpha. And this is related to what's called mutual coherence condition, where there's a number of other expectations on the structure of the problem, right? Which is the columns of phi not to be not like too parallel to each other, not too redundant. They're not orthonormal, but they're still expected to be spread out in the vector space. And then if we assume columns are normalized, columns of the basic function are normalized to unit length, and we can talk about inner product matrix of phi. It's called the Gram matrix, but don't worry about it too much. We'll cover this when we talk about kernels. Then the values of this matrix, inner product matrix, generalized inner product matrix, are the inner products between the i's and j's components of phi. The mutual coherence is basically defined as the maximum of the matrix. Right? It's easy to see that like the mutual coherence of orthonormal basis is 0. And if we have very similar columns, it's 1. And this m is essentially the quantity that goes to the left-hand side, right? So the conditions of exact recovery is related to what kind of basis functions we choose and how similar they are. The more similar the basis functions, the larger the value of m, then the more sparsity we can achieve, right? So if phi is very close to 0, meaning if phi is very close to orthonormal, then let's say m will be equal to 0, then alpha, this upper bound will be really big, right? So there is a trade-off. In other words, so there's trade-off between like the redundancy that we allow in our basis functions versus the sparsity in the solutions that we get. Meaning that if we don't allow any sparsity, then don't allow any redundancy in the basis functions, then the solution is not very sparse. Goes to say that like PCA projections are usually not very sparse at all. Neither is SVD. But if we have very redundant phi, then the alpha can be really sparse because, as you say, that if the basis functions have redundant information, we only need, if we know the projection on one basis, then we also know the projection on neighboring basis. We don't lose much information. So again, no free lunch in representation. So there's, we can have sparse coding, but we pay something by using non-orthonormal basis. So we're at time. These are the references that I was looking at. Some of them we talked about. Yeah, I hope you find this useful. We talked about autoencoders mainly and its applications. We talked a little bit about the problem of ICA, blind source separation, and we talked about what is a sparse coding look like. That's all. See you on Monday. We'll talk about mixture models, and hope you enjoy your assignment 1. It's due Monday. Cheers.
Hi, I may have a question.
Yes, go ahead.
Yeah, yes, I'm gonna ask a question according to the submission of assignment 1. And yeah, the two things I'm not quite clear. The first thing is the programming part, you can only including one person's name. So what if I submit with a teammate?
I feel there's 2 separate fields. I'm a bit surprised that yeah, we like the tutor hasn't answered. So basically, when you submit, Grayscope allow you to include your teammate's name. So make sure you include that.
Okay.
And the question inside with your UID, I believe, is for a different sanity checking purpose, and it will not affect attribution of grades.
Okay.
I hope that makes sense.
Yes.
Yeah.
And also we have to submit a contribution form. What it looks like, and shall we include them in the format of a PDF, or just how to submit that?
So that contribution is designated to be at the beginning of your theory part, which we assume is a written part anyway. So you just include 2 lines or something like that saying, okay. Yeah, person A and B worked on this, Johnny is submitting this assignment. You don't even say that because that's implied in your Grayscope credit. And you basically say person A focused on this part, person B focused on that part, or you can say A and B jointly discussed basically all parts, and then like you can say who wrote which part. I think this is for basically auditing purposes, that we wanted to strongly encourage all the teams to have almost equal contributions and not one person contribute a lot more than another person, right? So you can also say you've split up I know there is a lot of questions. For example, you can also work in a way where you split up the questions and then each person just checked, like thought about and written up the solutions for the different parts. Just say which, like person A worked on question 1, 3, 5, 10, person 2 worked on the rest, and then we sort of cross-checked and discussed the solutions, which is also a good answer. Because if the submission has your name on it, you better be able, so you're expected to be able to reproduce and explain all of it, even if one person did a particular part. You better check, and also include the discussion for the programming part as well, because we don't have a separate statement for the programming part, so one statement is enough.
Oh, yeah, thank you.
Yeah. So are people happy? that's the case, good luck with your assignment. And I hope to see many submissions. Like,
could I ask a question
Yes.
about submission?
Yeah, sure.
I just want to make sure, just one of the membership, the team member need to submit on the grid scope, or both of them need to submit.
So there's a Piazza, so don't submit 2 copies.
Okay.
There is this Piazza post. I can try and find which one it is. That basically says when you submit, you can say it's a team submission and who the team is. And after that, hopefully both of you can see the submission. I hope that's how Grayscope works. Yeah, there is also a rolling those components of assignment. There's a rolling thread about submission update and Siri. Right, so instructions for pair and group submission can be found in post 62 on Piazza. There is a screenshots about how exactly you do that.
Okay, thank you.
Yep. Yeah, if you submit 2 copies, the downside is that tutors and us will need to mark the 2 copies. And the potential risk is you might get different marks if we mark it twice. Of course, we don't like marking more. And the downside for you is one of them will get a lower score, which you don't want. All right, that's all for now. I made sure I recorded this time, and see you next week.